Good evening, good afternoon, good morning to the whole planet, to the whole ITTC community. My name is Leszek Wilczyński. I am speaking from Gdańsk, from Poland, and it's 1:45 at my place. So I am roughly in the middle of East and West as far as now is concerned. We are in front of the very interesting presentation by Technical Committee on Energy Saving Methods. The presentation will be given by Professor In-Won Lee from Busan National University from Korea. Energy saving methods was the topic for 2 periods in ITTC, and I think it has gained much wider understanding in last 7 years when we started with energy saving methods, and it is becoming more and more important issue, especially in marine transport. So Professor Lee, the floor is yours.
Thank you, Professor Wilczyński, for a wonderful introduction. Hello, everybody. My name is In-Won Lee, the chairperson of the Specialist Committee on Energy Saving Methods. It's my privilege to give my talk at the 29th ITTC virtual conference on behalf of the Specialist Committee on Energy Saving Methods. Our committee consists of 7 members. As you can see in the list, myself from Korea, Dr. James Goes from United States, Dr. Andrea Corrado from UK, Professor John Ting Chen and Professor Tia Lee from China, Professor Moneko Hinatsu from Japan, and Dr. Ramon Querada from Spain. We had 4 meetings so far, and I'd like to express my thanks to the hosts of the committee meetings and, of course, all the members of our committee. Okay, here you can see the terms of reference of our committee from the 28th ITTC. Tasks are generally the survey of energy saving methods, reviewing and developing appropriate guidelines for CFD, model tests, and scaling. Full-scale data is important, so we paid special attention to collect data regarding the energy saving methods. This is the second term for our committee, so we are supposed to wrap up our efforts so far and hand them over to general committees in the 30th ITTC. Each chapter in the final report and this presentation roughly corresponds to each task. Okay, let me move on to the chapter 2 regarding the survey of energy saving methods. In this shortened presentation, I'd like to make general remarks by showing you the category of ESMs, which are listed in the right. As a matter of fact, this category was established in the previous term, and it remains essentially unchanged. The primary category is about the principle, which means where the energy saving come from. There are 4 primary categories regarding this: the direct reduction, reducing propulsive losses, use of renewable energy, and operation shown next slides. Each primary category is subdivided into specific mechanism how the energy saving principle is achieved. During the present term, the committee searched for a new mechanism, so a couple of modifications have been made for the gate rudder and ducted CRP. This is the continued part for the category of energy saving methods. This is another general summary for the energy saving methods. This figure was taken from Bowman et al. In 2017, showing the performance of energy saving methods in terms of carbon dioxide reduction potential, published from 2009 to 2016. In this paper, the ESMs are categorized into 5 groups, such as hull design, power and propulsive system, alternative fuels, alternative energy source, and operation. And I believe this gives a good insight to the potential of the energy saving techniques. Okay, the next is the list of sources for the literature survey. This list encompasses relevant peer-reviewed journals and conference proceedings. Articles mainly published from 2017 to 2021 have been reviewed and summarized for this chapter. This is a continued list of conference proceedings for review. But due to the limited time for this presentation, I don't want to go into the details. So please refer to the final report for the review for respective article. Okay, let's move on to chapter 3, titled as Use of Wind Energy. According to Parker, there are several types of wind energy system. They are flattened rotors, kites or spinnakers, soft sails, wing sails, and wind turbines. Smith et al. In 2016 stated that wind propulsion is the most effective at slower speeds, for instance, less than 16 knots. And for smaller ships, for the dead weights of ranging from 3,000 to 10,000 tons. Those vessels account for 1/5 of global cargo ships. The typical energy saving effect by wind energy varies up to 2 to 24% for a single flattened rotor, and 1 to 32% for a towing kite, 10 to 60% for the econowind sails. It's a rather a large variation according to the literature. However, there is indeed a barrier to prevent wide adoption of wind energy solutions. These are unfamiliarity with technology, safety, and reliability concerns, and lack of demonstration. Therefore, more reliable, especially full-scale data needs to be obtained. The next slide lists the representative type of wind energy system and its energy saving effect. The first one is the wing sail, was investigated by Viola et al. In 2015, shown to reduce the thrust up to 10%. For towing kite, the percentage of fuel saving was predicted about 10% for Beaufort 5 scale, for 5 wind scale, even higher, as much as 50% at Beaufort 7 scale. For the flattened rotor, fuel savings ranging between 5.6% and 8.9% were reported by Pearson in 2014, Kraft et al. In 2014, and Luen Ringsberg in 2020. Okay, the next chapter, the next task for chapter 4 is to identify the necessity for new guidelines for CFD, EFD, and scaling methods. The first topic is about the CFD methods for energy-saving devices. The first topic is the Tokyo 2015 workshop on CFD and ship hydrodynamics, held at NMRI in Tokyo in 2015. The purpose of this workshop was the same as the preceding workshops, and it was to assess state-of-the-art of the contemporary CFD codes for ship hydrodynamics. In the workshop, 3 ship hulls were selected, and a total of 17 test cases were specified by the organizers. 30 groups submitted their computed results for 1 or more cases. Among the 3 ship hulls under consideration in the workshop, the Japan bulk carrier was associated with ESD, as shown in the lower right figure. The validation and CFD simulation and resistance and self-propulsion performance were carried out either with ESD and without ESD. The validation and verification results drew attention of the committee because they can shed some lights on the overall level of accuracy of CFD simulation. Comparison of numerical errors between the case with ESD And the case without ESD would imply how adequately the state-of-the-art CFD simulation deal with the propulsive performance of ESD. The next review topic of Tokyo 2015 workshop is the statistics of CFD parameters, which can give an idea on the best practice of CFD. Okay, this slide shows the comparison error in thrust coefficient and the grid uncertainty for thrust coefficient on the right. The major checkpoint here is to see whether the errors in ESD cases are systematically larger than those in no ESD cases. As you can see in these two figures, there is no clear evidence that ESD cases lead to systematically larger error or uncertainty. So the answer is no. And there is no evidence to support the inadequacy of current CFD technique in dealing with ESD. Therefore, the needs for a particular dedicated CFD procedure for ESD is not identified. Okay, the next slide is associated with the second review topic, the statistics of CFD parameters, which can give an idea on the best practice of CFD regarding the ESD simulation. The parameters under considerations are the number of grids, the world normal coordinate of work function y plus, the minimum and maximum location of the computational domain. So values for those parameters in all cases were compiled through a questionnaire by the organizer of the workshop. And as you can see here, there is wide variation in the parameters, which might cause the wide variation of the errors associated. Okay, the next topic related to CFD is to review a proposed guideline from PROD 2016. Hino et al. In 2016 presented a benchmark data for the validation of CFD simulation results for a Japan bulk carrier equipped with an energy-saving circular duct. In fact, this is exactly the same cases we've been reviewed through the Tokyo 2015 workshop. Okay, aimed at identifying the necessity to set up a separate guideline dedicated to ESD simulation. The committee had it reviewed by multiple of CFD experts in academia and industry. The guideline section in Hino et al. Was compared with the following existing ITTC guidelines related to CFD. It was found that some of the statements in the proposed guidelines are not included in the existing guidelines. On the other hand, it also can be said true that those suggestions are largely well known in the CFD community. In addition, it is hard to ascertain that the guideline by Hino et al. In 2016 took into considerations for the relevant aspects of diverse types of ESDs, because only the circular duct was dealt with. In consideration of these points, the committee concludes that it's premature to set up a CFD guidelines dedicated to ESD in the absence of reliable database of CFD as well as EFD results for various kinds of ESD. Okay, let me move on to the next topic in the experimental methods section. Okay, skin friction reduction is one of promising techniques of ship energy saving, and air lubrication has been implemented in several tens of vessels so far. In 2017, the previous term, ITTC adopted a recommended guideline, resistance and propulsion test and performance prediction with skin frictional drag reduction techniques as a guideline to extrapolate model test results to a full-scale performance prediction. However, the model test procedure for air lubrication in real practice has not been standardized yet, which may cause a significant deviation in the model test results among model test organizations. So the committee was asked by the advisory committee to give more detailed description of model test procedure on the air lubrication techniques, such as test conditions. So the committee carried out a survey to investigate the current status of model test practices involved with air lubrication among organizations. 12-item questionnaire was distributed and 11 organizations replied it. The following summarizes the replies. Here we summarize the major questions in this presentation, so please refer to the final report for full questions. For question number 4, regarding the ship type considered, bulk or cargo carrier and tanker are the most frequent choices. About scale factor, in question number 5, the majority was ranging from 10 to 50. The next item was injection pressure. In most cases, number 3 was selected, which means pressure was set at the hydrostatic pressure in moderate scale. Also, arbitrary pressure and no idea also indicated. For question number 8, choice number 2 was mainly selected. Injection flow rate in the moderate scale was usually controlled to give the same film thickness as in the full scale. For question number 9, the choices varied between no extrapolation, ITTC-78, and own guideline. It's notable that the newly adopted guideline has not been selected so far. This again proves the absence of standard procedure related to the air lubrication model test. Okay, the next chapter is about the recommended guideline from the committee. It is titled as a scaling method for ship wake fraction with pre-swirl devices. The purpose of this guideline is to complement the ITTC-78 procedure for the prediction of the delivered power and rate of revolutions for single and twin screw ships with either pre-swirl stator or pre-swirl duct being installed. Okay, let me begin with explaining wake scaling issue of ITTC 1978 related to pre-swirl devices. Pre-swirl device generates a counter-swirl flow to save rotational energy from propeller. For the prediction of powering performance, ITTC-78 method adopts the thrust identity method to find out the effective mean wake fraction. This is effective in the situation like figure 30A. The difficulty in scaling arises from the point that the pre-swirl device makes not only a counter-swirl, but also axial flow retardation. It is therefore necessary to decompose the axial and tangential components separately. As shown in figure 30B, the presence of pre-swirl device causes the relative velocity to propeller blade to change as UR prime with increased angle of attack, alpha plus delta alpha, thereby increasing thrust. If the scaling is applied to the total amount of model wake based on the thrust identity in the ITTC-78, this might result in overestimating axial induced velocity UX prime as in figure 30C. Thus, the increase in thrust due to both axial and tangential induced velocity might be misinterpreted solely by the axial induced velocity by ITTC-78 methods. This inadequacy of 78 scaling has led to attempt to propose a new scaling in 1999. That approach, which is generally called ITTC 1999, was based on the report of the Specialist Committee on Unconventional Propulsors. Among two approaches, the method B, where the stator is considered as a part of the hull, is now commonly referred to as ITTC 99. The major difference compared with the 78 method formulation is the term W sub ms minus W sub mo. Here, the stator action was considered to be mainly of a potential nature because the main effect of stator is to increase the angle of attack of the propeller blade. Therefore, the difference in wakes with and without stator is directly transferred to full scale. Well, even though this might be more reasonable than ITTC-78, but this can account for the viscous nature of axial retardation. So there comes a new guideline. With a view to improve both ITTC-78 and ITTC-99, there has been a series of researches in which axial wake and tangential wake are separately treated according to ship type and device type. For instance, pre-swirl duct is adopted for fuller and slow ship like tanker, while pre-swirl stator is employed mainly for slender, faster ship like container carrier. Kim et al. In 2017 presented that the portion of the increase of angle of attack by axial and tangential flow is different for PSSD or PSD. They proposed a scaling formula shown here. This is a compromise between 78 and 99 method in that the axial velocity component and tangential velocity component are scaled separately. The axial wake, being of viscous nature, is scaled following 78 method. On the contrary, the tangential wake is not scaled following after the assumption of ITTC-99. It was found that the portions of tangential and axial velocity vary according to the vessel type as well as the device type. Shown in this table, it was proposed the factors of axial and tangential portion to be 0.3 and 0.7 in PSS, and 0.8 and 0.2 in PSD cases, respectively. But it's worthwhile to mention that the factors in table 2 have been derived from limited ship types, namely KCS and KVLCC. So generalization towards identifying reasonable value range for each factor based on more case studies with more ship types is necessary. Okay, I'm considering I'm behind schedule. Let me briefly mention the full scale data. Okay, the importance of full scale data is in proper assessment of ESM cannot be overemphasized, but full scale data is very rare, so we always need relevant full scale test campaign for energy saving methods. Okay, the first category is energy saving device. The most notable literature is Hassler and Yan, which is the part of the EU's GRIP project. Okay, for 52K bulk carrier, about 6.8% energy saving at trial condition was reported. Okay, the next topic is direct reduction by air lubrication and low frictional coating. For air lubrication, De Freitas et al. In 2019 introduced the full scale data air lubricated 40K chemical tanker and showed about 5% energy saving on the average. They stated that the ISO 19030 and basis of data filtering is currently only viable means of executing analysis performance of the ESM under consideration. The second topic, Cho et al. In 2021 carried out the evaluation of the performance of frictional drag reducing AF coating based on ISO 19030 standard. It is notable that they were able to isolate the effect of drag reducing coating by comparing two identical fresh coated vessel condition just after redocking with only coating being changed. So they indicated that the coating leads to a speed increase of 3.7%, which is approximately equivalent to power saving of 11.7%. Okay, this is the last slide. The potential task for the next committee is to continue to monitor the development of relevant techniques for ship energy saving and identify the needs to complement the present EEDI framework. The second, identify the necessity of guidelines for CFD methods, model test and scaling for energy saving devices. Number three, collect full scale data obtained through relevant benchmark tests. Finally, I'd like to point out recommendations to the conference. The 29th ITTC Specialist Committee on Energy Saving Methods recommends adopting the new guideline on scaling method for ship wake fraction with pre-swirl devices. Okay, that's all I have today, and thank you very much for your attention.
Thank you very much for a very interesting presentation. So far, we have got a question from Didier Frechot. The question is, could some of energy devices have an effect to delay cavitation inception? If yes, would be a minor effect or not?
Well, the effect of energy saving methods on cavitation inception has not been quite active topic of review for our committee. Okay, perhaps it is concerned that maybe the air lubrication might promote the cavitation inception, but personally, I don't think that's the case. And and for other types of energy saving devices like the pre-source stator, maybe the other committee, like the performance of ships on service, or combined EFD and CFD, or maybe resistance and propulsion committee, there might be some relevant literatures which can shed some lights on that matter. Yeah, that's it.
Thank you very much. There are, oh yes. We have a question from Jin Bao Wang from Marik.
Okay.
If left side is PSS, the right side is PSD, how to correlate?
Which slide do you mean? Left side, right side?
I don't know.
I don't know which is left or which is right.
Okay, so maybe Jin Bao will become more specific. In the meantime, I have a different question.
Okay.
Do you have any evidence, or have you met any evidence of the energy saving devices that failed? That instead of giving energy saving, provided troubles.
You mean structural failure or performance failure?
Performance failure.
Performance failure. Okay. Well, there has been some literatures pointing out the problem of the difference of performances according to the different drafts. Okay. Usually, energy saving devices are designed under the design draft. Okay. But I remember that there is some literature pointing out that sometimes energy saving device didn't work properly. I mean, the energy saving efficiency became negative for some other draft. Okay, so yeah, my answer is yes, and that's usually came from is associated with the different flow field associated with different draft, I think.
Okay, and was this effect predicted by model testing or not? Or there were no
well, usually model test didn't cover all the drafts. Okay, usually design load draft performance was mainly tested and they reported or published it, but later the speed trial revealed that in other drafts the effect usually the far smaller than the so-called optimal draft reported.
Okay, we have got a message from Jin Bao, so I can combine two of his messages.
Okay.
If left side is PSS and the right side is PSD, the left is port, the right is starboard. How to correlate?
Well, okay. So you combine the port side and starboard side, different type of the energy saving devices.
Yeah, I guess so.
Okay, that's a kind of the unprecedented type of energy saving devices. Perhaps, yeah, personally, I haven't seen such kind of example. But yeah, well, I think yeah, it's a very good idea because, as you know, the wake field behaves differently on the port and starboard side. So yeah, so that's the as you know, the main reason why we developed the asymmetry pre-swirl data. So yeah, that's a very interesting and an innovative idea, but I haven't seen the literature for that example. Okay.
Thank you very much.
You're welcome.
There are no more questions posted, and I think we have eaten the time for the session already. Thank you very much, Professor Lee, for
thank you very much, everyone. Yeah.
For the excellent work. Thank the presenters, asking questions, and to the audience. Goodbye.
Goodbye.